Hey everyone, it's Mr. Glover here. So today we're going to start trigonometry. It'll be a really short jaunt because we've only got a couple of days of material for before the end of the year, but I wanted to give you a bit of information on some unit circle trig, and I want to get through at least radians because I know that's something you'll need in the future if you study more math. So let's talk a little bit about unit circle trigonometry. A bit of this will probably be reviewed from last year, but we are going to go in depth and we will go at a much faster pace than you would have in grade 11. So the idea with unit circle trig is this idea of taking triangles that you've been dealing with since middle school, like right angle triangles, and we're going to take concepts like plotting on the Cartesian grid, which is something that you've been doing for a long time as well, and we're going to stick them together. We're taking a triangle and we're placing it on a grid. So now this is like an amalgamation of your classical trigonometry that you've done before, as well as graphing. So we've got to define a few things. So in standard position, an angle has 4 parts. It's got the initial arm, a standard position angle, a terminal arm, and a terminal point. The terminal arm is like a ray that comes out from the origin, and it is a certain length. It's whatever length the distance from the origin to this point is. This is what you call the terminal point. It's going to have a coordinate x and y, and we'll call it point P. You will have some angle that this ray makes with the x-axis. We'll call that theta. That's going to be your standard position angle. And the initial arm is the x-axis. So this idea, and normally what I would do is I'd have you make one of these, and you actually have like a thing that you can rotate. The idea is that you've got this ray coming out at some specified length, and you can rotate it around the x-axis or the Cartesian grid until you reach a specific angle. For example, this is 90 degrees, this is 180 degrees, this is 270 degrees, and this is 360 degrees. And anything in between falls in one of our quadrants, either up here or over here, or maybe down here. The angle is always measured from the positive x-axis, so the initial arm, and you do get shapes that don't look like your standard triangles because they're not triangles, they're just angles measured at standard position. So like, for example, I could measure this angle. That's going to be an angle somewhere around 300 degrees. Because that's not a triangle though, we have to create a triangle on the grid somewhere, and we use what's called a reference angle to deal with it. A little bit more information. Cartesian grid is split up into 4 quadrants. So there's quadrant 1, quadrant 2, quadrant 3, and quadrant 4. So they're counted counterclockwise. And I've got symbols in here because this is supposed to represent x and y. So in quadrant 1, x and y are both positives. In quadrant 2, x becomes negative while y is positive. In quadrant 3, they're both negative, and in quadrant 4, x is positive while y is negative. This is going to be something that comes up, and this is something that, that plays a part in our solutions. Also recall that a reference angle is an angle from the terminal arm to the x-axis. So for example, let's draw an angle. If this is our grid, let's say that we have a ray that comes out over here somewhere, and it goes to this point P. We can measure our angle in 2 ways. We can measure our angle from the positive x-axis, so we can measure this angle. That's what you call the standard position angle. But we could also measure to any x-axis, so we can measure to the closest one, which is right here. This is what's called the reference angle. The point of a reference angle is it allows you to create a triangle with the x-axis at any point in time. So for example, this one, you'd have a triangle right here. We're still dealing with the standard position angle, and we have to keep in mind that the reference angle can only give us values that are positive. Like we could solve for this side of the triangle and we could solve for this side, but because we're in quadrant 2, whatever I get for my x value, I know has to be negative. So you can work with reference angles using trig you've done before, but you have to kind of take your answers and then put them through that filter of, well, what does it mean in the context of this question? All right, so let's try it. We're going to define what are called trigonometric ratios, and then we're going to find some trig ratios at a specific angle. So the primary trig ratios are sine theta, cos theta, and tan theta. These are all things you've dealt with before. You've probably used something called SOHCAHTOA, but this is just a relabeling. These are actually trig ratios. The ratios of x to y, or the ratios of sides of your triangle, and they're trigonometric ratios. So a terminal arm of length 1 has a standard position angle of 45 degrees. Find the primary trig ratios of that angle. So you can do this a couple of ways. I want to show you the way to do it exactly, but you can use a graphing calculator to kind of cheat. First thing we're going to do is graph our angle. So we've got an arm of length 1 that makes a 45-degree angle. It's going to look something like this. It's got length 1, and this is a 45-degree angle. That should bring a bell in your mind because there's two triangles you need to remember. There's two special triangles. There's the 1, 1, root 2 triangle. So let's maybe draw them both at the top. There's the 1, 1, root 2, and these are not drawn to scale. This happens to have angles of 45, 45, and 90. We also have what's called the 1, 2, root 3 triangle. And now this one, I think it comes up later in the note, but we can do it right now. But 1, 2, root 3. And this has angles of 30, 60, and 90. If you forget, one's 45, 45, 90, one's 30, 60, 90, and the largest angle is going to be opposed by or opposite of the largest side. So the smallest angle, 30, is opposite of 1, and the largest angle of 90 is opposite 2. Anyways, we want to focus on this one. So a terminal arm has length 1, find standard position angle of 45 degrees, find the primary trig ratios. Okay, so we need to find sine, cos, and tan of 45. Okay, so I know that sine is opposite over hypotenuse. So sine theta is going to be opposite over hypotenuse. That's going to be 1 over root 2. Okay, and cos theta, cos is opposite over adjacent. So it's opposite over adjacent. From 45 degrees, that's 1 over 1. Which is, or wait, I'm getting this backwards. That's 10. This is not opposite over adjacent. This is adjacent over hypotenuse, so CAH, which is 1 over root 2. Tan is opposite over adjacent. Which is 1 over 1, which is 1. Sorry about that. One other thing, another way to think about tan, and you probably haven't seen this before, tan theta is actually defined as sine theta divided by cos theta. That's what tan is. So you can take the same ratios and plug them into this formula, 1 over root 2 over 1 over root 2, which is 1. So that's 2 ways of finding tan. All right, if we redefine these trig ratios so that they're consistent with x and y rather than opposite, adjacent, and hypotenuse, we can find trig ratios of any angle in standard position. And so for any angle, theta, in standard position, where theta is between 0 and 360, terminal point P with coordinates x and y, primary trig ratios are defined as cos theta, which is x over r, sine theta, which is y over r, and tan theta, which is y over x. I've literally just taken SOHCAHTOA and I've labeled the 3 sides x, y, and r instead of OA and R, or C. So if you draw this, draw a triangle, This is x, this is y, and this is r. It's just SOHCAHTOA with different labels. But r is the square root of x squared plus y squared. If the angle theta is not in quadrant 1, for example, if it's not between 0 and 90 degrees, we can use reference angles to find the primary trig ratios. We have to be careful though, as x and y are not always positive in every quadrant. And this is what I was talking about on the first page. So let's try a question where this becomes an issue. Terminal arm of length 1 has a standard position angle of 195 degrees. Find the primary trig ratios of that angle. So we're going to draw our triangle, and we need to remember 195 is going to be in quadrant 3. That's because this goes from 0 to 90, this goes from 90 to 180, and this goes from 180 over 27. So we're going to have an angle somewhere down here. It's probably going to be something like this. Okay. Now, in standard position, if I were to measure this from here, this would be 195 degrees. But I don't really want to work with my standard position angle. I want to work with what's called a reference angle. So I want to work with just that angle. If I know that it's 180 all the way to the x-axis, this is just 15 degrees past 180, or you can take 195 and subtract 180, and we're left with 15 degrees. So I know I've got a reference angle of 15. So now I can figure out what my trig ratios are, and I can work backwards to figure out what my sine lengths are. I also know that this is a side length of 1. So using our calculator, if I know that sine theta equals y over r, I know that y equals r sine theta, which is 15. R is 1, so this is just 1 times sine theta equals y. And I can figure out what my y value is by just calculating sine theta in my calculator. When you are working with graphing calculators, I think they will default to radians, so you have to hit the mode button and make sure that you're in degree mode for now, or everything will be wrong. So I'm just going to calculate sine of 15, and that gets me 0.259. So I found one of my side lengths. Technically, this is going to be negative, so I probably should have given myself a little more space in my drawing, but say that this is my y value. Well, my y value is going to be negative 0.259. That's because we're in quadrant 3. You do the same thing with x. So x is going to be our cos theta, which means 1 cos, sorry if you can hear that in the rain, it's just hammering down there. R cos 0, 115 is x. And you end up with x equals 0.966. But again, this is just in terms of our reference angle. So anytime you do this, you'll always get positives if you use reference angles. You've got to remember, we're in quadrant 3. Quadrant 3 has negative x values, so our x value is negative 0.966. We've now got all 3 sides of our triangle, and we can build any of our trig ratios, which, I mean, technically we kind of have them, but that's fine. So sine 15 is given by y over r. Y is negative 0.259. R is 1. So sine 15 is just negative 0.259. This is different than just sine of 15 because that would be positive 0.259. It's a minor difference, but it makes a big difference in terms of your actual answer. Do the same with cos and tan. Excuse me. So cos 15 is x over r. X is is negative 0.966. And R is 1. So cos 15 is negative 0.966. Lastly, we can do this with tan. Tan of 15 is given by y over x. Technically, if you were to take y over r for sine and x over r for cos, it'll cancel into y over x. Put in our numbers. Y is negative 0.259. X is negative 0.966. And we get 0.268. And I mean, you could have just calculated sine, cos, and tan of 15, but you're not going to necessarily get the right answers because some of them will show up as positives when they should be negatives. So far, we've concerned ourselves with angles between 0 and 360, but we're not limited to these angles. If we continue to rotate the ray around the origin, we can make any angle that we like. For example, let's say that we have a ray that goes around twice. So I'll show you the ray. It's going to go around once. It's going to go around twice, and then maybe it goes back up here. So when I go to measure this in standard position, it gets kind of confusing, but it goes around once, twice, and it connects here. So I know that that angle is going to have to be somewhere greater than 720. It's going to go all the way to 360, all the way to 720, and now this is probably like 750, something like that. Sometimes these angles will overlap. Angles in standard position with the same terminal arm are called coterminal. So to give you a quick example, we'll just pick the same kind of triangle. We've actually got a ray that goes up like this. One angle is going to be measured in standard position. One angle is going to be measured like that. And since this ray shares two different angles, we could call it, we could call this one theta 1, we could call this one theta 2. These are coterminal. So theta 1, theta 2 are what you call coterminal angles. Determine the measure of all angles in standard position between minus 1,000 and positive 1,000 that are coterminal with 150. So this seems like quite a daunting question, but it's actually pretty straightforward. We have an angle that is 150, so it's an angle, if we draw it, it's going to appear over here somewhere. We need to figure out all the angles that are between negative and positive 1,000 that match up to this. Positive angles will be measured counterclockwise, negative angles will be measured clockwise. So we could draw a whole bunch of different angles. We could go around to there, or we could count backwards, and that's another angle. They're all coterminal. So what we're going to do is we're going to split this up. We're going to go from 0 degrees to 1,000 degrees, and then we'll go from negative 1,000 to 0. From 0 to 1,000, we've got the first one, it's 150. If you want to find something that's coterminal to that, it has to go around the circle one whole time. To complete one revolution, you go through 360 degrees. So the next angle is going to be 150 degrees plus 360 degrees, which is 510. So that's another coterminal angle. We can do the same thing, but we can add 360 twice. So we can go 150 degrees plus 360 degrees times 2. And this gets us 870. We can keep doing this until we get outside of our range. And in this case, this is as far as we go, because another 360 puts us past 1,000. To get negative angles, we just subtract. We just go around the circle in the opposite direction. Instead of going around counterclockwise, we go around clockwise. So again, we start with 150, but now we're subtracting 360. That gets us to negative 210. Again, we can do the same thing, but we can subtract 360 twice. So 150 minus 2 times 360, which is negative 570. I think we still have room to do this one more time. So we can subtract 360 again, 150 degrees minus 3 times 360. And that gets us to negative 930 degrees. So all of these angles are coterminal because they all share the same ray. And all of them fall within this range of values from negative 1,000 degrees up until positive 1,000 degrees. I should point out that there's infinitely many angles. You can keep looping around the circle infinitely many times and make new angles. Numbers keep going, they don't just stop. But usually you'll be given a specific range of values that you have to solve for rather than give me all coterminal angles, because technically there's no answer to that. You can write it in a general form with like a formula, but that's it. All right, here's a little nifty application of unit circle tree. Suppose the terminal point P is in any quadrant lies 1 unit from the origin and that P is rotated through 360 degrees. We can use the Pythagorean theorem to relate the radius of the circle to the coordinates of P. So let's draw a little sketch here. Okay. I'm going to try my best to draw a circle. Actually, you know what? I don't have to. I think Desmos does that for, or Notability does that for me. Except I didn't line it up. All right, pretend that's perfectly aligned. So there's our circle. If we take a ray, that's radius 1, and we rotate it around the circle, that ray always has the same radius. It's going to have radius 1. It's going to go through the entire 360 degrees, and if you were to put like a tracking dot on the end of the ray, it's going to basically sweep through our circle. So our circle holds this relationship between our 3 variables. We've got variables x, y, and r. So we can use Pythagoras. And we can just use a squared plus b squared is c squared. And then we need to relate this to our situation. We're not dealing with a, b, and c, we're dealing with x, y, and r. So x squared plus y squared equals r squared. And if we plug in the fact that r has to remain constant, x squared plus y squared equals 1. That is the equation for a circle with radius 1. That's what you need to do to plot it. Some of you might have done this already when you did your Desmos project earlier in the term, but we can now plot this, and I don't think I will because I don't want this video to take a long, long time. But what you'll find is that if you solve for y, so if you were to write like y equals square root of 1 minus x squared, you'll end up with half the circle. And then if you solve for the other half, negative square root of 1 minus x squared, and you plotted both of those, you'll get a circle. I think the top one will give you the top half, and the bottom one will give you the bottom half. And then the net result is a circle with radius 1. You can change that radius, pretend that's nice and centered. You can change that radius, and you'll change the size of your circle. So the center circle of origin, or centered at the origin, and radius 1 has the equation x squared plus y squared equals 1. You can use the fact that x equals r cos theta and x or y equals r sine theta to define 3 more trig ratios. So suppose point P, given x, or given coordinates x and y, is the point where the terminal arm of theta intersects the unit circle. The reciprocal of cos theta, and I don't know why these are named this way. I always make this really clear to people. I think they're named stupidly. You'll see what I mean in a second. There's probably a Latin reason or a historical reason why, but I feel like this was a pretty big miss. The reciprocal of cos is called secant. And secant is given by 1 over x, which is 1 over cos theta. Okay? The reciprocal of sine is called cosecant. it's given by 1 over y, which is also 1 over sine. So honestly, the way I remember this is that they're backwards. There's probably a real reason, but I think of them as, well, cosecant should have been the reciprocal of cosine, but it's not. And secant should have been the reciprocal of sine, but it's not. And if I could remember that they're backwards, then I usually can figure out that cosecant is related to sine. It's not ideal, but it works. Reciprocal of tan is cotangent. And this is x over y, which if tan was sine over cos, this is cos over sine, which is also 1 over tan. All right, recall the 1, 2, root 3 triangle. We kind of did this already, so I'm just gonna write the triangle here so that we have it as a reference, because we're gonna need it. 1, 2, 3, and 30, 60, and 90. Determine the exact values of the 6 trig ratios for 5, 10. So first we need to draw 5, 10. It is going to, well, let's figure out what quadrant it falls. We go up to 90, up to 180, up to 270, up to 360. So we're not here. If we added another 90 to that, we'd go up to 450. If we added another 90 to that, we would get up to 530. So I know it's in this quadrant. It's going to be over here somewhere. Okay, if we want to draw it in standard position, go around the circle. And, that's where the snap feature doesn't work that way. So that's 510 degrees. But we need to know what our reference angle is. Okay, so if we recognize that 360 is here, and if we added another 180 to 360, we get up to 540. What am I saying? We get up to, 540. 540 is all the way. We've only gone 510, so we are 30 shy. And if you want to do the math on it, you could just say 540 degrees, which is what would get us back to the x-axis, minus 510 degrees, gets us a reference angle of 30. So now we can deal with this nice triangle rather than dealing with our other 510 degree angle. Okay, so we need to figure out what x, y, and r are, and then we need to just plug them into our equations. I know that for the 30-degree triangle, we have 1, 2, and root 3. But we also have to remember we're not in quadrant 1. So we can fill in these sides, but we don't necessarily have positives everywhere. My radius r is going to be 2. My y value is going to be 1. But my x value is going to be negative root 3. And that just has to do with the fact that we're in quadrant 2. Otherwise, it would have been positive root 3. Once we have all 3 of these sides, we can simply just plug these into our formula. So we've got 6 trig ratios to do. We've got sine theta, which is y over r. We have cos theta, which is x over r. We have tan theta, which is y over x. And then we have all the reciprocals. So there's cosecant theta, which is r over y. We have secant theta, which is r over x. And we have cotan theta, which is the reciprocal of y over x, so it's x over y. And we just plug these in. Y is 1, r is 2. So sine 30 is 1/2. Cos theta is x over r. X is minus root 3, r is 2. So this is negative root 3 over 2. Tan is y over x, which is 1 over negative root 3. Cosecant is r over y, which is 2 over 1. which is just 1. Secant is r over x, which is 2 over negative root 3. And cotan is x over y, which is negative root 3 over 2. Or sorry, 1. Negative root 3 over 1. And there you go. There's all 6 trig ratios. It seems like a daunting task, but once you unpack the question, draw your diagram, figure out the reference angles, it actually becomes a fairly simple question if you understand what the recipes are for each of these ratios, and if you have all 3 sides. It all comes back to this. I think we'll skip this one just in light of time. Give it a try on your own. It's going to be the same thing, except rather than measuring your angles positively, you're going to be measuring your angles backwards. So maybe I'll get you started on it. Instead of going counterclockwise, you're going to be measuring your angles clockwise. So you would go all the way around the circle to 360, and then you're going to go another 56 degrees. So it's probably going to be down here somewhere. We can extend our equation of a circle with radius 1 unit circle, or sorry, we can extend our equation of a circle with radius of 1 unit to a circle with any radius by changing our formula. X squared plus y squared is r squared, where r is going to be the radius rather than 1. Okay, the point P, which is negative 2 and 5, is the terminal point of angle theta in standard position. Determine the exact values of 6 trig ratios for theta. So this is the same type of question as before, but rather than being given the angle, you're given a point. You solve it in a similar way, but you need to find x, y, and r rather than just know them based on the angle. So start by drawing our point. It's point minus 2 and 5, so it's going to be over here somewhere. It's actually going to be up here, but do it like this. Now, negative 2 is the x value, and 5 is the y value, but I don't know what r is. So I need to use Pythagoras. If x squared plus y squared is r squared, then r is the square root of x squared plus y squared. Plug in our numbers. X is minus 2, y is 5, so this is the square root of negative 2 squared plus 5 squared. And you will find that r equals the square root of 29. No, it's not a nice number. Keep it as an exact value. Don't turn it into decimals. So this is root 29. Now we've got all 3 sides. We've got x, y, and r. So we just need to build our trig ratios. Again, sine theta is y over r, which in this case is 5 over root 29. Cos theta is x over r, which is negative 2 over root 29. Tan theta is y over x, which is 5 over negative 2. And now, well, we should probably do it the proper way. Once you know sine, cos, and tan, you just flip them upside down and you've got secant, cosecant, and cotan. Or sorry, cosecant, secant, cotan, but we'll do it the proper way. So cosecant theta is r over y, which is root 29 over 5. Secant theta is r over x, which is root 29 over negative 2. And cotan theta is x over y, which is negative 2 over 5. However you want to do it, it will work, but you do need to make the first 3 trig ratios to get the next 3. All right, we're going to try one more problem. This one's going to be a bit of a doozy. This one's tricky, but it's based on the same type of thing. Additionally, we can use one trig ratio to work backwards and determine all other trig ratios. So instead of being given an angle, instead of being given a point, we're given a trig ratio, we need to use what we know about that trig ratio to find the side lengths, and then once we find the side lengths, then we can go ahead and we can solve this question. All right, so we've got cosecant equals 3. Determine the exact values of the other trig ratios from 0 to 180, and then determine possible values from 360 to -360. Okay. So start by writing out what our angle is. We have cosecant theta, that equals 1 over sine theta, which is r over y, which we are given is 3. Okay, so this equals 3. Now we can remember that this is also 3 over 1. Okay, so it becomes clear to us that we have a radius of 3 and we have a y value of 1. Your radius r can never be negative, but your y value could be. So if you run into like a tangent, for example, where you have x and y, you have to take into consideration that both x and y could be negatives. But in this case, y is positive, y is 1, and r is 3. Okay. So based on what I know, I've just found that r equals 3 and that y equals 1. All right. So now I need to find my trig ratios. We could draw this if we want to, but I think we can just figure out what x is and then find the trig ratios. So we're going to use Pythagoras. We need to find x. X squared plus y squared equals r squared. I don't know x, so I need to move everything to the other side. X squared equals r squared minus y squared. And then take the square root. X equals the square root of r squared minus y squared. X equals the square root of 3 squared minus 1 squared. Or x equals root 8. Okay, now we can build our 6 trig ratios. So we've got sine, cos, and tan. Sine theta is y over r, which is 1 over 3. Cos theta is x over r, which is root 8 over 3. And tan theta is y over x, which is 1 over root 8. Okay. For the next 3, let's just do what I talked about last time. The reciprocal of sine is cosecant. So we just flip this. This equals 3 over 1. The reciprocal of cos is secant. So we just flip cos, 3 over root 8. And the reciprocal of tan is cotangent. So cotan theta is root 8 over 1, which is just root 8. So there we go. There's question A. We've got all of our trig ratios. Oops. All right, now question 2 is where it gets a little tricky. Question 2 says, determine the possible values of theta in the domain from 360 or minus 360 to positive 360. Okay, so what we need to do is we need to draw the triangles first. What we know is that we've got a radius of 3 and we have a y value of 1. So part B, if y equals 1, then theta has to be either in quadrant 1 or it's going to be in quadrant 2. And I probably should have done an equals. We'll just do that. Theta is either in quadrant 1 or 2. 3 and 4 have negative y values, so they're not possible. So let's draw what we know. Okay. So now I know that these are my 2 options. We've got a radius of 3. We've got a y value of 1. I don't really need to draw that in. I suppose we could. Maybe we will. okay? And either of these two sides could be our answer. So we're going to get multiple solutions. We could have this angle, theta 1, or we could have this angle, which is, we'll call it theta 2. Okay, now remember, those are reference angles. Those are not our total angles. And actually, what am I saying? They're both going to be the same reference angle. Theta 2 is going to be this. So then the question becomes, what is our reference angle? We've got to work backwards. If we have sides of 1 and 3, well then we can use SOHCAHTOA, we can use sine to solve for theta. So I know that sine theta equals y over r, and I already know that sine theta equals 1 over 3. So that means theta equals arc sine of 1/3, or 19 degrees. Okay, so I know that theta 1 is 19 degrees. Maybe we'll draw this again over here to make it a little more clear. So one of my options is this triangle here, and it's got 19 degrees as its reference. Okay. So that's one of my answers. Theta 1 is 19 degrees. Theta 2 is my standard position angle of the other possible answer. So we've got a triangle over here. It has a reference angle of 19 degrees. We need to know what angle is this. There's a couple ways to do it. We could figure out how far we are, and then how much more it takes to get to 180. What I would probably do is I'd just take 180 and I would subtract 19 degrees. And we get an angle of 161. All right. So now it appears like we're done, but we've got to, don't worry, there's more. We've got to go back and look at our domain. We just found the angles from 0 to 360. We did not find the angles from negative 360. So what we can simply do is we can just measure them backwards. It's going to be kind of weird. So this is purple. One of our angles is going to go from the origin to this ray. We'll call that theta 3. And one of ours is going to be going from the origin all the way around to this ray. We'll call that theta 4. Okay. So now, theta 3 is 19 degrees past 360, or 180. We've gone negative 180. We need to go another 19. So theta 3 is just negative 180 minus 19. And it's going to be 199, negative 199 degrees. Theta 4 is 19 degrees shy of negative 360. So theta 4 is negative 360 plus 19. And you're probably going, why is one subtracted and one added? Well, this one we continue going counterclockwise, so we're subtracting. This one we're stopping short of 360. So we're at. We end up with negative 341 degrees. So this is a hard question. These are typically, there's going to be something like this at the end of most sets of notes, and I guess fortunately for you, you probably won't finish this unit because of all the changes that have happened. But typically you will see a lot of questions similar to this, and they're all going to be sort of varying depending on what we're doing in that given section. So just to kind of rehash what we did. We started by using our trig ratio to figure out what x is. We knew that r is 3 and y is 1 because our ratio is r over y. Then we used Pythagoras for x. We then used the recipes or the formulas for sine, cos, tan, cosecant, secant, cotan to define those trig ratios. Part B, We drew our triangles, knowing the fact that we had to have a y value of 1 and a radius of 3. And that's only possible in quadrants 1 and 2. We then drew every possible angle in standard position that falls in the range from -360 up to +360. So we've got two positive ones, one from the positive x to the first ray, one from the positive x to the second ray. And then we did our negative angles, starting at the positive x, counting backwards to the second ray, and starting at the positive x, counting backwards to the first ray. It's kind of weird, and you've probably never thought about stuff like this before. But this is unit circle trig. This is weird stuff, and it's one of the coolest units in my opinion. It's also one of the units where people have a really difficult time because it's very abstract and it's hard to wrap your head around the concepts. So I've got a few questions for you to try. This will be one of your last assignments this year. Page 474, 3 to 8, 9 to 11. I plan on doing some more notes on on radians, which is kind of like degrees. It's just another way of measuring angles, because those of you that are going to go off to university will definitely be using radians, and I don't want you to go without having to say that. At that point, we might stop the unit. We'll see how things are going and see where everybody's at. Anyways, I'm going to stop the video now. Hope you all have a great rest of the day, and if you've got any problems, just shoot me an email, and I'll do my best to try to answer it for you. Okay, bye for now.